Welcome back to my channel. So today we're going to be solving exponential and logarithmic equations. So let's go over the exponential equations first. And this is just a general strategy. What I want you guys to think of this list as is kind of like a menu of options. So every equation is going to be a little bit different. And these are just some general strategies that can be helpful. You're not always necessarily going to be going down this list in order or anything like that. It's just we're gonna see what works for the equation we're looking at. So the first thing that's pretty easy to do is if you can isolate an exponential on one side with a number, that's pretty nice. And then if you can recognize a common base, so if you can isolate your exponential and then recognize that the other side can also be put in terms of that base, that's a really nice situation to be in. Another option is that you can take a log of both sides. So you can always do this option. And sometimes it'll be nicer, sometimes it won't be as nice. But if you can take a log and use log properties to get your variable out from the power of your exponential, that's a nice option. And lastly, you can change bases if you need to. So if for some reason you have different exponentials, like a 2 to the x and a 3 to the x in the same equation, it might be to your advantage to go ahead and change the base of one of those to match with the other one. Possibly. Not always. So let's jump in and do some examples. So let's start off with the easiest one here. Checking this out, notice how we have our one exponential term, 4 to the 2x. There's our exponential. You see how the x is in the exponent? This is definitely an exponential equation. And looking at both sides, I notice that the base here is 4, and this looks like it's a half. But I kind of feel like I have an opportunity for a common base. So the common base that I'm seeing here would be 2. So take a second and think about how you might write both sides as a power of 2. So on the left, I could write 4 as 2 squared. And on the right, I could write the 1/2 as 2 to the negative 1. Okay, so I haven't changed the equation, I've just changed how it looks. And then using my exponent rules, I see that I have both sides written as 2 to some power. Okay, so logically think about it. I have both sides of the equation are equal. I have the bases are equal. So logically, that must mean that the exponents are also equal. That must mean that x is equal to -1/4. Right? And for exponential equations, the domain of an exponential is all reals. So we're not concerned about the ability to have an extraneous solution in quite the same way that you can get with logarithmic equations, but it is a good idea when solving an equation. If you have time, you can always check your solution by plugging back in. I'll let you guys verify that. Let's move on to our next example. So this one's cranking up the difficulty a little bit. I see my base here is e. And already I can tell there's not going to be a way to write a number like 4,000 in terms of e. So this one we're definitely not going to be able to do that same trick as we did last time. This might be a situation where we're going to want to take a log of both sides. But before I jump into doing that, I definitely want to at least isolate my exponential. So I want to get rid of that 2,000 out front and make this as clean as possible. So if I divide both sides by 2,000, I've at least isolated my exponential. And I have a coefficient of 1, that's nice. And now I can take a log of both sides. Now you're allowed to take any log base you want, but some choices are easy and some choices are just a little bit harder. So for this particular equation, the base that we're working in is e. So it makes a lot of sense that I would take log base e of both sides, the natural log. So when I take the log base e of both sides, this is what it would look like. And remember from the last video about log properties that when you take a log base b of b to the x, they're inverses, they undo each other, so that would just be 0.1t. You can also think of that as doing the power rule and then simplifying. That'll also get you to the same place. So you'll get 0.1t equals ln2, which means that t equals ln2 over 0.1. Which is, your textbook would simplify that as being 10 times ln2. They would simplify the fractions there. Either one's fine with me. Okay, so let's move on to a little bit harder example here. Okay, we have a combination. We have two different exponential terms added to each other. It looks like the base is the same, but the thing that makes this equation a little bit more intimidating is there's not really anything we can do to isolate our exponentials as one term. And you can't, if you take a log of both sides, you can do it, but it won't be particularly helpful because you can't use log rules to simplify it further. So at this point, the only thing I know how to do is maybe there's some sort of algebraic manipulation I can do. So I'm rewriting it, and I'm noticing that the negative exponent would mean that e to the x is in the denominator of a fraction. So maybe one thing I could try is multiplying both sides by the term that has the variable. To see if this equation perhaps cleans up a little bit and becomes something I can work with. So that e to the x distributes to both terms. I'd get e to the 2x plus 15. And then I have 8e to the x and I have 2x and x. So this one I flagged as a little bit more challenging because this equation has a special kind of phenomenon going on. This is actually a polynomial, specifically a quadratic in e to the x. Some people will call them quadratic types, but the most formal way to define it is a quadratic in e to the x. So what that means is, you see how we have that pattern of squared, single. It's like having x squared, x, and then your constant. So if I just treated this as a quadratic, we can do something called a u sub and say, well, this is going to act a lot like u squared minus 8u plus 15. And we could solve that equation in terms of u and kind of take like a multi-layered approach to solving. So if I solve this with u, this factors as u minus 3 times u minus 5. So my solutions for u would be 3 and 5. And remember what u was standing in for. U was standing in for e to the x. So my solutions would be, taking the ln of both sides, I have now easier equations that I can do this on. X would be ln 3 and x would be ln 5. So those are my two solutions to the equation. So let's just go through that one more time, kind of explaining what we did from start to finish. Okay, so to start with, taking the log of both sides wasn't going to be helpful. So I rewrote it in another format that helped me see that I actually had my variable in the denominator, and then I treated it as a rational equation. And when you have your variable in the denominator, it often makes sense to try and multiply your fractions to prevent that from happening. So I times by e to the x, both sides. And then what happened is a polynomial, a quadratic in terms of e to the x, popped out. Some people at this step don't do the u sub, they'll just literally factor it. So they'll just like jump to the step where they say, oh, that's the same as e to the x minus 3, e to the x minus 5, and then they'll do that instead. That's okay. If you're really, really slick with your factoring, you're probably at the point where you can see that that is, as a matter of fact, how you would factor that with e to the x. But otherwise, the u sub tends to be what's a little easier for people. And then we got easier equations to solve. For e to the x, we took the log of both sides and we got our two solutions. So let's move on to logarithmic equations. Okay, again, we have a menu. View this as a menu of options. Not all of these things are going to work for all the equations. It's going to be kind of a see what works for each equation. And the one thing to note with the logarithmic equations is that we are going to always be checking our solutions. So we're always going to check our solutions to make sure that we're not getting extraneous solutions, which you can kind of think of as false positives. And the reason that there are extraneous solutions for logs is basically because log terms don't have domain all reals. So you might remember way back when we said you can't plug a 0 or a negative into a log. That's because the domain of log base b of x is all x values greater than 0. So because of that, we got to be careful that when we plug something into our original equation, that it's within the domain of that equation. So noting that we're always going to check. Now the rest of these strategies are just what's going to work on a case-by-case basis. So the first thing to try is maybe you can straddle your log terms and get one log term on each side. Maybe it's not immediately obvious that's going to happen, but maybe you can condense your logs to make that happen. Another thing you can do is you can apply an exponential to both sides. And then last, you can try changing bases. Perhaps that'll be helpful. And again, some equations you're not going to do all these steps on. So let's take a look at some examples. So to start with, we're going to solve algebraically ln of 8 minus x squared equals ln of 2 minus x. So I see that I have a log term straddling both sides. Some people will just instantly write the next thing. They'll say, okay, if you have the same base and you have the log terms equal to each other, so my base is e, my logs are equal to each other, it must be the case that 8 minus x squared equals 2 minus x. The hidden step that they're doing is they're applying e to both sides, and the e and the ln are canceling. We don't always write that, but that's what's happening mathematically. So now I have an equation that's no longer logarithmic, all the logs are gone, and it's just a quadratic. So this one we can handle. If I move my x squared over here, I'd get 0 equals x squared minus x minus 6. This factors as x minus 3 and x plus 2. And then our solutions would be x equals 3 and negative 2, but we need to check. So when we check, we're going to plug in and see. If I plug in a 8 minus 3 squared is 8 minus 9, does that equal ln of 2 minus 3? Yikes! We got a negative. Just having a negative, even on the left side, would be bad enough. So we got to cross out 3. 3 is not actually a viable solution. Let's try the 2. When I plug in a 2, I get 8 minus 4, and on the right, I get ln of 2 minus negative 2. Perfect. So that one works out. We only have the one solution, which is just negative 2. So let's just write, this is what would happen with an extraneous solution. That x equals 3 here was an extraneous solution. Okay, so let's move on and solve the next one. So moving on to the equation, ln of x plus 1 minus ln x equals 3. If I try and get logs straddling sides, that's not going to work because I have 3 terms here, but I can condense logarithms. So if I use my log rules, condense completely, it would condense as ln of x plus 1 over x equals 3. And I could then, I don't have straddling log terms, but I could still use that trick of raising both sides as the power of e. And then on the left, the e and the ln cancel. So I get x plus 1 over x. And on the right, I get e cubed. And that's a whole number. I'm only writing it this way as a fraction because I see I have x in the denominator. And this would be a rational equation where it's useful to cross multiply. So cross multiplying is kind of a shortcut trick for multiplying by the least common denominator. And that's what we would get. Now remember, to solve this equation, I want to get variables on one side. So I'm going to get my x's on the left, my numbers on the right. And then I notice that x is a common factor, so I can factor that out. So I get x equals negative 1 over 1 minus e cubed. And when I plug that in, I want to make sure that that is going to be, now it initially looks negative, but make sure that when you actually calculate what that is and plug it in, that it is going to be in fact a positive number. And it looks like it will be because I know that e cubed is for sure bigger than 1. So I have a negative on the bottom, negative in the numerator means this is going to be a positive number. So when I plug that in back to my original equation, I'm not going to have a negative or 0 in the logarithm. But again, you guys can take the time to carefully check this. That's the kind of thing you'll want to do at the end of a problem, you know, when you have time and before you turn your test in. Okay, let's take a look at the last one here. So this is our challenge mode for logarithms, and I wanted to choose another one that looked kind of weird. This one is going to be harder than some of the other ones because you see how we have this squared here? Got a squared right there. And this is a log raised to a single power. This looks like a polynomial. So this looks like we have u squared minus 2u minus 15 equals 0. So that looks like it would factor like plus 3 minus 5. So my solutions would be negative 3 and 5. And remember that that is standing in, u is standing in for log x. So which equation has a logical solution? Can a log be equal to a negative number? Yes, it can be equal to a negative number. You can't plug in a negative number to a log. So how do we solve it? Well, the base here that's unwritten is 10. So if I raise both sides as the power of 10, I'll get my solution. So I get x equals 10 cubed, or sorry, 10 to the negative 3, and x equals 10 to the 5th. And then we'd check and make sure that those are actually solutions to this equation. And I've already checked them, and it turns out that both of them are, but you guys can verify that yourselves as well. So let's talk about some hypotheticals. Some hypothetical questions that students frequently ask me is they'll say, okay, so what if I go through all this hard work and all of my solutions end up being extraneous? It's definitely possible. That can happen. That means your equation has no solution. So I will just say that no solution is a possibility. Okay, it's still important for you to know that an equation has no solution, though. So thinking about where you guys are going to be encountering equations will be coming up as a direct result of real-life phenomenon. So it is important to know that if you have an equation that has no solution, it's going to tell you something about the real-life circumstance. So having no solution isn't like, oh, well, that was a waste of time, like, why did I do this? It's an important decision. It's an important conclusion to come to, basically. And another question that people will get is, how common it is. It's really hard to break things into percentages and say oh, it happens exactly this amount of time. I would say that it can definitely happen, and just if you feel like you're getting all extraneous solutions, it is possible that you made a mistake and that's why they're feeling like they're extraneous. So I would definitely check your work carefully if you're getting that your problem has no solution, but it can happen, so I can't say that it'll never happen. Okay, so hopefully this was helpful, and I'll see you guys next time.